So, this is a brief recap of whatever I talked about yesterday, at least half of it, the Lagrangian part. Just to remind you, we have this action which is an integral over time of L q dot t. This integral of course has to be done over a path q of t, and of course the moment you specify q of t, q dot t automatically gets specified by that. So, action ultimately is a functional of q of t, and the most common thing that we do with the action is we vary the path, we change the q's to q plus delta q's. So, qi becomes qi plus delta qi, and q dot I automatically becomes q dot I plus ddt of delta qi. So, the moment you vary this path, the velocity automatically varies along with it, and if you take this, plug this back into the action, you see that the first order variation in the action works out to be this expression. The minus sign is there simply to sort of avoid a minus sign here, nothing else, minus dt delta qi ei plus this term which is a boundary term, which gives you the values at T2 and T1, and if you insist that you are only going to talk about variations which vanish at the endpoints, that extra term vanishes. So, this term is not there as long as delta qi vanishes at T1 and T2. So, if you make this demand on top of everything else, this term drops off, and the extremization of the action delta A equals 0 automatically tells you that as long as the delta qi's are all independent, that is you can change qi's independently, then each of the ei's would have to vanish, which are our familiar Euler-Lagrange equations of motion. And because L is in general a function of q dot and t, and so is del L del q dot, this can be expanded out in a form which has an acceleration term times del 2 L del qi dot del qj dot, and a term which is free of the acceleration. So, this is how I have split up the Euler-Lagrange equation of motion terms. All the ei's are basically wij qj double dot plus ki, and wij we worked out, and you all know this is going to be del 2 L del qi dot del qj dot, and ki is the rest of the term, which you get by doing a ddt of del L del q dot I, and this is the whole nasty looking expression, which essentially means just this term expanded out with the q double dot term taken separately. Okay, so, the Euler-Lagrange equations of motion tell you that wij qj double dot plus ki has to be 0 as long as the equations of motion are obeyed, and from a bad habit which we inherit from particle physics, we call this an on shell. On shell basically is the on mass shell thing that particle physicists talk about, and so we sort of inherit that term. Frankly, here the shell really means that part of the configuration space, q dot space, where your trajectory lies. Now, as we said, standard theory would usually apply to a situation where determinant of this w is not 0. This implies you should be able to solve for the q double dot j's from this as functions of q dot and t. So, we will get n, if you have n degrees of freedom, you will get n second order differential equations, which you would typically solve. And given under most situations, these equations would have solutions which exist in the region given by t between T1 and T2, our limits that we are talking about. And typically, you would need, in order to solve them, the 2n initial conditions. The simplest ones would be 2n initial coordinates and initial velocities. They are easy enough to calculate with. More complicated would be boundaries, say n values at the beginning, n values at the end. Sometimes that runs into trouble, but we are really not bothered too much about that right now. Okay. Now, today our main concern will be a situation where this does not work. If determinant w is not 0, is actually 0, then this fails. You will not be able to solve for all the accelerations in terms of the coordinates and the velocities. So, the standard thing that you get, n second order differential equations which you want to solve, will not work out. Okay. We will see explicit examples of this, but before that, let me just make a few comments about the general structure of the theory. That may sound a bit abstract to begin with, but with examples, I think it should be clear what I mean. Okay, so if the determinant is 0, that means basically rank of this matrix W. Okay, what does that tell you about the rank? The determinant vanishes. It's less than the dimension, right? It's less than n. And actually, if you have this rank, let's call this RW just for reference, then it also tells you something about the nullity. You are familiar with the rank nullity theorem? So basically, nullity is the dimension of the null eigenspace, the space of all vectors which would vanish when W is applied on them. And this nullity works out to be simply n minus RW. That's the rank nullity theorem. If you have a rank, so basically it says the moment RW is less than n, you have zero eigenvectors. And therefore, zero eigenvectors, I don't mean eigenvectors which are 0, of course they can't be 0. I mean eigenvectors whose corresponding eigenvalue is 0. In fact, this is exactly the number of independent, in the sense of linear independence, of course, null. I'm not going to call them 0 eigenvectors simply because I will need 0 for other purposes later. So W has a finite number, n minus RW number of independent eigenvectors corresponding to eigenvalue 0. Now notice that if I have such an eigenvector, which is typically given by an equation like this, now, right? I is the ith component, alpha is just a label of the eigenvector. So alpha runs over 1, 2, all the way up to n minus RW. You have this many independent eigenvectors, and when you multiply Wij by Vi, I have done it on the left here for reasons that will be clearer maybe tomorrow. But this is a symmetric matrix, so any right eigenvector can also be rewritten as a left eigenvector. So not really a big issue right now. Okay? Now what will the Vi typically depend upon? What does Wij depend upon? What are the functions? They are not just functions of Q, they could also be functions of Q dot. Right? If you start with a quadratic Lagrangian in Q dots, then double derivative would give you something which does not have Q dots in them. But not all Lagrangians have to be quadratic in Q dot. So in general, Wij will depend on Q and Q dot, not on Q double dot, which Ei also has in it. And since Vi's are basically eigenvectors of this matrix, they will also, of course, depend on Q and Q dot. Okay? Now, an immediate consequence of this, well, this is actually not even a consequence of this statement. This has to be 0 on shell anyway, right? That is, if I think of the E1, E2, E3, all these Euler-Lagrange equations of motion as components of a vector, and then dot it with this V vector, I must get 0, right? On shell, because on shell the E's are 0. That's it. So for this, you don't even need this. But the fact that the Vi alphas give you 0 when contracted with Wij has an immediate consequence. Remember, Ei is basically Wij Qj double dot plus Ki, right? Wij's depend on Q and Q dot, Ki's depend on Q and Q dot, right? And the only Q double dot difference, the acceleration dependence, is here in this term, right? So if I contract this with a Vi alpha, and I am of course going to get 0 as long as we obey the equations of motion, what happens? This term, the term with the acceleration, drops out, right? So this thing, which we can call the alpha function phi, will depend only on Q and Q dot, right? Not on Q double dot, because the Q double dot term has dropped out. So ultimately, what does this give us? It tells us that for each of these V's, each of the n minus RW V's, I will end up with a function of q and q dot alone, which has to vanish the moment equations of motion are satisfied. Okay. So now, in the usual scenario, q and q dots don't have any equations between them. Q double dot is what you get out of the equations of motion. They tell you how things change. But the moment you have a constrained system like this, where determinant of W is 0, the immediate consequence of that will be you will have some relationship which q and q dot will automatically have to obey to begin with. Okay? So you will have a bunch of constraints between the q's and q dots. You cannot independently give, say, the initial velocities and initial positions, for example. Okay? Right? So any questions about this derivation so far?
Sir,
yeah.
Can you repeat how is this expression not dependent on q double dot?
Because this term, in EI, you had a q double dot term, which actually was this wij qj double dot. The ki, the rest, only depended on q and q dot, right? So when you contract vi alpha with this whole thing, the whole thing is EI, and EI is 0 on the shell. But when you contract vi with that, vi wij is 0, right? Those are what the vi's are. They are the null eigenvectors of W. The fact that W has null eigenvectors is a consequence of this determinant being 0, right? And because if you have a rank RW, then you have this many independent null eigenvectors. So you, in principle, you could have this many independent functions, each of which would contract to 0, which give you 0. Yeah.
The inverse is also true, right? Given there is a relation between q dot. Can I see the determinant of W?
So if there is a relationship between q and q dot which has to be obeyed for all time, then you would be right. Then that would actually tell you that W would actually have a null eigenvector. Now, this is a bit abstract, so let's try to make this a bit more concrete. Today I will take a look at a few examples. Okay? Okay, let's now try example 1. And this is where my bad habit of not bringing notes is going to come back to bite me. Because one problem is signs matter in all of these. So if you get a plus sign instead of a minus sign, things might completely go out of the window. Now, by the way, if anybody is getting very impressed by the fact that I am working all this out on the board without looking at notes or stuff, that's because I have worked it out for 4 hours before I came to the class. Okay, so it's just that I don't really have an organized enough note. I should have definitely brought this. Anyway, let's try this. This one is an example of. I am, of course, borrowing these examples from a textbook. I think, I will be in deep trouble if I were to quote the name of the textbook because I'm not very sure I'm doing it right. But I think it's Roth and Roth. And the name is Classical and Quantum Theory of Constrained Dynamical Systems. Of course, I'm going to talk about the only first few chapters of that book. This book essentially talks about quantization of constrained dynamical systems, which is something we sort of should equip you for through these 5 lectures. Now, this example is taken from that. Now, let me just work out this, try to solve this problem using standard methods. So, P1 or Px here would be del L del x dot. You can all tell me what that is. By the way, you should all keep check as to whether I'm doing the algebra right. My algebra is notoriously bad, and if I mess up the sign here, the whole class will go out of the window. So please pay attention and catch me out if I'm making a mistake. So these are the 2 conjugate momenta. For us, these conjugate momenta are really not important right now, except as stepping stones towards writing down the Euler-Lagrange equations of motion. So E1 or Ex, let's call it E1 anyway. And just to sort of lay the groundwork for what we are going to do maybe at the end of today's class or maybe tomorrow, this is where we will start, I'm writing E1 0. The 0 has a significance, we will come to that later. Right now, just think of that as an idiosyncrasy. I just put in a 0th order thing in top. So this will be x double dot plus y dot ddt of px minus del L del x, right? Right? That's what the equation of motion is. So I'm just writing that down. Del L del x will come from here. Del L del x is of course x minus y, but it's minus del L del x. So this is my E1 0. So E2 0. Py dot of course gives me 0, but I have to do minus del L del y. And minus del L del y will give me minus x dot. And this one will give me plus y minus, no, plus x minus y. I hope I've got this right. Please keep track, because if I mess up here, it's going to be very bad in the long run. Okay. Now, you can easily see that you cannot solve for the two accelerations here, right? Y double dot doesn't even appear in this equation. Not only that, it's also easy to see that the second equation here is a constraint equation. Minus x dot plus x minus y that has to be 0. That's a connection between only the positions and the velocities. So not like a standard second order differential equation that we get. We're going to get a constraint between the positions and the velocities given by this equal to 0, right? Because that's what the equation of motion is. Both of these are going to be 0. I have one which looks like a genuine equation of motion. The second one doesn't. This is a constraint equation. Okay? And just to sort of connect this to the null eigenvector thing that I talked about, can anybody tell me what W is going to be? You can immediately read off W from the ease. Is 1 0, x double dot, no y double dot, and 0 0, right? Now this obviously has a 0 eigenvector, which is 0 1. And if I take this vector and dot it with the E vector, which is just these two components, I'm simply going to get this thing equal to 0. Of course, here I didn't have to work at all. Like the moment I wrote down E2, I could see that this 0 is a constraint. But in general, it might very well happen that you will have accelerations all over the place in all the equations. But if you have a null eigenvector, the moment you contract the E vector with that, you are going to get an equation which only has x's and x dots, or q's and q dots in general. Okay? So our general theory at least works here. This is such a simple case that I didn't even need the null eigenvector to figure out that this is a constraint. I could see it directly. Yeah.
Do you have to take Helmholtz conditions here?
No. You start with a Lagrangian, whatever you get has to be consistent with Helmholtz conditions. Helmholtz conditions work the other way around. You start with an equation, you want to write a Lagrangian for that you need Helmholtz conditions. Here the only thing you have to check with is, are these giving you meaningful equations at all or not? Even if they satisfy the Helmholtz, these will satisfy the Helmholtz conditions, but they may still give you inconsistent results. They won't here, but let's just see. Okay, now that we have constraints, things seem to make life difficult for us. Actually, it doesn't. In this case, at least, it makes life a lot easier. But let's see one thing. One constraint that we get is this one, and this immediately tells me that I don't have to solve for y separately, right? Y is simply x minus x dot, right? So if I find x, I have found y. Okay, so that makes our life a lot easier actually. Then, okay, so can we find x? For that, what we need to do is take a look at this equation. Okay, so x double dot, let's get rid of the y completely. Y dot is, this is y dot, right? And minus x plus y, what is that? That's actually nothing but x dot, right? Okay? This is 0. That's my first Euler-Lagrange equation of motion where we have used this thing. Actually, what we have really used is something slightly more sophisticated. The point is, this constraint is valid not only at a particular time, this is valid at all times, right? The equation of motion has to be satisfied at all times, which means not only is this constraint equal to 0, its time derivative also has to be 0, right? So time derivative of a constraint also has to vanish at all times. That can, and sometimes very often does, give us additional constraints. So when we do this in a systematic fashion, and the 0 I have written down there is basically an indicator that that was a 0th level constraint that you will get. Then from that you will get first level constraints, second level constraints, and so on. Right now this problem is simple enough that I don't really have to bother doing all of this. If I just plug this in, I end up with a very, very simple equation. Oh, right? No. I get the simplest possible equation that you can have. And what that means is, the moment you have a y which satisfies x minus x dot, the other equation is automatically satisfied. So what's the most general solution for this? X is some function of x of t, y is a complete solution of the problem. But you have to see one thing, that even by maintaining the initial conditions, so what are the initial? First of all, the moment you have constraints, you cannot put down arbitrary initial conditions. So at t equal to 0, whatever y is, has to obey this equation for all times, including at t equal to 0. So y at 0 must be given as x at 0 minus x dot at 0, right? Without that, this will not be consistent. But once you have that, there are infinitely many x of t's which will actually give you the same x of 0, x dot 0, right? In fact, write down any Taylor series you want with the x0 plus x dot 0 into t and finish it off any way you want. All of these infinitely many problems will satisfy the same initial value condition. So unlike usual situations where the initial value tells you exactly what the solution is, here you don't have that. What you have is something actually even more interesting. Suppose I have a solution, x of t and x of t minus x dot t. And then because I know that I can change the x of t, let's say I change it to this. Okay? And at the same time, I change y. I change y to so if this xy's extremize my action, I change x by an arbitrary function of time, change y by a connected function of time. Not the same one, but something which the moment you have alpha t, you know this one as well, right? And you still have another set of x and y which extremizes the action. Okay? And this exactly is what you call a gauge symmetry. A local gauge symmetry, something where you can change things at all times, right? And still get a solution, still get an extremum of the action. Clear? Yeah.
I have a question. So, if one is given a Lagrangian with symmetry, then the corresponding merger, the corresponding quantity is 0. Isn't that a constant equation for such a Lagrangian?
If you have a gauge symmetry, well, that actually is not always 0. That depends on the gauge symmetry you have. But the fact that if you have a gauge symmetry, it essentially tells you that you cannot possibly have an x of t uniquely given by the initial conditions. That's what gauge symmetry essentially tells you. And that also tells you that it should not be possible for you to find out all the accelerations as functions of q dot. So this procedure, which is usually used, must break down somewhere. And where it breaks down is basically by the fact that this w is no longer invertible, and the moment w is not invertible, you will get constraints. Okay. Now, in fact, here I could have figured out this particular gauge symmetry. Now I have to be a bit more careful. I don't want it to go out of the board. By essentially figuring out, suppose I change to x plus delta x. Let's forget about this result that we have figured out here. We had explicitly, this was a simple enough problem where we explicitly solved the equations of motion and showed explicitly that if you change x of t by an alpha t and y of t by an alpha minus alpha dot, the new x and y will also again extremize your action. That is, will also give you solutions to the Euler-Lagrange equations of motion. Let's see how that works out. Suppose I had not done any of this. But I just put in an arbitrary delta x and arbitrary delta y and try to figure out how much the Lagrangian would change. That's easy enough. At least first order calculations are easy. That's going to be x dot delta x dot plus x dot delta y plus y delta x dot, right, plus x minus y to delta x minus delta y, right? That's the first order variation. It's very easy to write down. Okay? Just the change in the square is, well, twice the value into this, it's just a plus b whole squares formula. Now, if you collect terms together, you see x dot comes with the coefficient delta x dot plus delta y here. Y comes with the coefficient delta x dot minus delta x plus delta y. Now, the dots are important, so I hope the dots are visible. And you also have an x, a minus x, which comes with delta y minus delta x. The reason why I put in delta y minus delta x there is because I have a delta y minus delta x here as well. So it's easy for me to factorize. All I'm going to do is just some simple algebra. Since I'm very bad at doing algebra in my head, I'm just going to sort of write it out explicitly. So it's easy to see basically that all of these terms almost have the same change, right? Delta x dot minus delta x plus delta y. Of course, that's not true. This term is not there, so I just have to put it in. Y has the term, and x minus x, well, I have to put in the delta x dot plus minus delta x plus delta y. But that means I have actually put in this minus x delta x dot extra, so plus x delta x dot. So what has happened at the end of the day is that I've ended up with a variation in the Lagrangian given by x dot plus y minus x to delta x dot minus delta x plus delta y plus these two additional pieces, which together is just ddt of x delta x, right? Now, notice that this actually tells us that if I do a variation of x and y where delta y is given by delta x minus delta x dot, this term drops out. So then the change in the Lagrangian becomes just the total time derivative, and that means the action will not change as long as you ensure the delta x vanishes at the two ends, right? Clear? So this form makes it clear that there is a symmetry here. I can change x by anything you want and change y by ddt of delta x, and that is going to give you a new solution. If you had an extremum before, now you again get an extremum. So the gauge symmetry is that we talked about. You can see that directly by varying the Lagrangian. It's just that here the Lagrangian was simple enough, so you didn't have to resort to any complicated trickery to figure this out. Could explicitly solve the problem, but didn't get a solution in the sense that you couldn't get a pin down unique solution. You just got any x of t will work as long as you keep the initial conditions right. And the moment you have an x of t, any smooth x of t will work. It needs to be differentiable at least once. And then y of x of t minus x dot t will also work. Now, these features were simple enough to work out here just by almost by inspection. In a more complicated problem, it will not be that easy to figure them out. So there is a step-by-step standard procedure which we can follow. But before I go to the step-by-step procedure, let me show you a couple more examples so that this sort of thing is driven home a bit more. Okay. Now, so this is example 2. Another Lagrangian. Well, essentially the same Lagrangian, right, except that I hope I have not written the same one by mistake. No. The potential energy term has a different sign. Of course, this has to be squared, this has to be dot, this. So, the kinetic energy part, that part which has the velocity in it, are the same. The potential has changed sign. The reason why I am going to show you this is you will see that some of the features that you saw in the previous problem will not come here. It will be different. And when we do the general procedure, then the procedure will tell you why they are different, but here we have to just work it out. So, now here again P1 is x dot plus y, P2 is 0, and E1, the 0th order E1 is going to be x double dot plus y dot, and now comes the difference minus, this will be plus x minus y. So, this is 0, and E2 0 will be minus x dot plus y minus x. I hope my math is right now. So, we will proceed in almost the same way as we did before. What did we do earlier? This is the constraint equation. In fact, I know that the second equation will give me the constraint equation, right, because I knew that W here is the same, right. The kinetic energy term is what gives you W. So, W is 1 0 0 0. The null eigenvector is 0 1. If you contract the E vector, which is a vector with these two components, with that you are going to get E2, right, the second component. And this, of course, obviously is a constraint. It's a relationship between x dots, x and y's. But now, the change is very subtle and very small actually. Y works out to be what? X plus x dot. It was x minus x dot before, this now is x plus x dot. But now let's plug this back here. What do we get? X double dot plus y dot, which is x dot plus x double dot plus x minus y, and x minus y is minus x dot, right. So, like we had in the previous case, we do get cancellations, these cancel, but now I get x double dot has to be 0. So, unlike in the previous case where plugging the constraint equation back in the first equation essentially rendered that into a non-equation, an identity, here that no longer happens. Tells you that A, x of t has to be, and y of t well, the A and B are constants which you can figure out from the initial conditions. So, here unlike in the previous case, the initial conditions completely determine your solution. The moment you have the correct initial conditions for x and y, I say correct because the x initial conditions and y initial conditions have to be connected by the constraint. You can't just give arbitrary initial values for them, but as long as you have given a constraint initial conditions which satisfy this constraint at t equal to 0, you get a unique solution out of this. This one does not have a gauge symmetry. So, it is not really correct to say that all singular systems have gauge symmetries. This one does not. We will see once again this is just an advertisement for a more step by step procedure which will reveal the gauge symmetries at the end. But that is a bit more abstract, so I decided to use some examples first. So, it is not true that you will always get a gauge symmetry. This one does not have a gauge symmetry. Yeah.
Can you classify when you get gauge symmetry?
Well, you mean can you just take a look at the Lagrangian and immediately say? The answer is no. But can you figure that out? The answer is yes. There is a procedure which you will follow, and we will do that in steps. Yeah. Any questions?
So you use the word gauge symmetry. So we say gauge symmetry if we declare that the solutions map, solutions that maps one.
Yeah. So yeah, let me just remind you. In the previous case, you had two solutions. This y was x minus x dot, and then if you change x by something, So you change x by something which is t dependent. In field theory, when we say gauge symmetry, we usually mean x t dependent, but here it's only t dependence. And change y by something which again is t dependent, but of course connected to this one. That anyway is not a problem, right? Because even in standard say U1 theory, you put up a space-time dependent phase on your wave function. You have to change the a by a term which depends on that whatever you change you have made, right? So the point is there is an arbitrary space-time dependent function which governs how the x and y changes. That's what a gauge symmetry is. Local gauge symmetry is. When I say gauge symmetry, I really mean local gauge symmetry.
So you don't need to say that these two solutions are supposed to be identical?
They are not identical. Of course not. The alpha, as long as alpha is not 0, they are not identical solutions.
No, they are not identical, but when we say gauge symmetry, we mean that those solutions are
Depends on your situation. When you are looking at the equations and looking at the solutions are identical. When you say in electromagnetism, when you say two different potentials connected by a gauge transformation, they are not identical potentials, and even quantum mechanically they might have different consequences. But classically they give you the same electric and magnetic field. Okay, in that sense they are identical, but they are identical as far as the consequences, not identical as far as their mathematical form is concerned.
When you say gauge symmetry, you mean this one, not
I mean, can I change my Lagrangian, can I change my coordinates, can I do a transformation of coordinates and the action stays invariant? That is the general meaning of the word symmetry in this context. In this limited context, I am not talking about the physical meaning of these things. That will of course depend on the precise physical situation.
Here you work with unreduced phase space.
Yeah.
Solutions will be only identified with partially reduced phase.
True, but that is the kind of gauge symmetry you are talking about. I am defining gauge symmetry to be a situation where you are starting with your configuration space. Can you change your configuration space variables in a time dependent manner, different values at different places, and still get a solution? That actually is exactly what you usually do in gauge symmetry as well. There, of course, your functions would be xt dependent, but that's also here x and y are basically two different x's in that context.
There
Yeah.
are real physical systems where, depending on how you look at it, these solutions are just different.
Yeah.
Just different quantum states.
Exactly.
For example.
Exactly. So it's not always necessarily true that changing the gauge will not change the physics. In some cases that's true, but that in general gauge symmetry is a much more general thing. This is a general example of a gauge symmetry. Okay. Now I want a vote. Do you want to see more examples explicitly worked out now, or do you want to see the general procedure? One more example. Okay, only one person says one more example. Physical example, no. Unfortunately, the problem is all of the examples I'm going to work out will look like very trivial and rather stupid examples for one very simple reason. I'm working in point particle dynamics alone, just to keep things simple and not talking about field theoretical changes. In field theory, these same things go over in almost all physically important examples. Okay. Since I'm not doing field theory, the examples I'm going to give you, okay, if you want me to give you a physically important example, I will tell you, look at the Lagrangian for electromagnetic field. That will give you a perfectly wonderful physical example. Okay. But that will have mathematical complications, essentially due to the fact that now you're dealing with infinitely many degrees of freedom and stuff like that. So because I want to talk about simple situations, I will have to talk about problems which may look a bit artificial, not very physical. But that's simply the price you have to pay for trying to oversimplify the thing and talking about a simple situation.
I have a question.
Yeah.
Really a trivial one, but you are considering some alpha, I mean the change, what you call the gauge. So it is maintaining, a priori this is the constant equations. Let's say.
Has to maintain the constraint. It has to actually maintain all the Euler-Lagrange equations. One of them is the constraint equation.
Yeah.
The point is, this satisfies both of the Euler-Lagrange equations provided y is x minus x dot. If you change it this way, the new x and the new y will also satisfy both the Euler-Lagrange equations, not just the constraint equation. But the constraint equation is one of the Euler-Lagrange equations, so that has to be satisfied anyway.
Right. So basically, so then this in this example, the alpha should satisfy this alpha double dot should be 0.
No,
But
why?
is the equation of motion?
We saw, not for this one, by the way. Sorry, you missed the point, I guess. This was a second example which did not have a gauge symmetry. The first one had a gauge symmetry. There this equation, instead of giving x, you are right that if x double dot equal to 0 had been the equation ultimately, then the only possibility would be alpha double dot equal to 0, which essentially means that alpha is automatically fixed by the two initial values. So once you have fixed the initial values, there is no freedom left. You don't call that a gauge freedom. The second problem did not have a gauge freedom. The first one did. This is for the first one. After talking about the second one, I went back to the first one to illustrate the issue about the gauge symmetry. The second one did not have a gauge symmetry. Most singular systems will have a gauge symmetry, but not always. And as I said, there's a procedure for figuring out these gauge symmetries systematically. But okay, before I go there,
The examples we are choosing, SN is very obviously 0.
yeah,
In general, it can be a function of q dot and the determinant.
yeah, it will be more complicated to work with. So the in general, it could be a pretty complicated function of q dot which still vanishes.
The determinants are
Yeah.
or all.
Yeah. So one slightly non-trivial example, which actually is a trivial example if you think about it. If this had been your kinetic energy term, the Hessian would have been 1, 1, 1, 1, right? Determinant 0. And here is sort of obvious that x plus y dot is being squared here. Here is sort of easier to see that the trickery that's going on there, at least. So Amol, you had some.
In hindsight, looking at these two examples, would you have guessed which has a gauge symmetry and which doesn't?
Well, that's guessed, I don't know. Guess, I don't think I would be able to guess. At least the second one, the first one, I showed you the gauge symmetry just by calculating delta L and showing that delta L could be made into a total time derivative if you chose your delta x and delta y just right. Now that, of course, because I know the answer, it's easy for me to sort of reconstruct that algebra. Now, if I don't manage to get that, that could mean that I'm being stupid and I'm not seeing something which is there. It could simply mean that it's not there. So that is why we need a systematic procedure for figuring out whether this can be done or not be done. Okay? Yeah.
When you were doing it in the variation of the Lagrangian way, did you use the equation of on-shell part somewhere? Or
No.
You did not?
No, I didn't. I didn't. The only thing I used was delta x has to vanish at the ends.
Yeah, so that's fine.
But not the on-shell part. So the gauge symmetry actually works off-shell. That's the point. The gauge symmetry ultimately works off-shell. That's actually what's going to come out of this. You don't need the equation of motion for that. Okay, now just one more example, perhaps example 3, which looks nasty. This actually has a physical application, but I'm not going to talk about the physical application at all. This is a theory which you get when you create an effective theory from a field theory. So this has a genuine physical application, but right now for us this is just a Lagrangian. I've just written down q2 dot minus e to the q1 whole square plus half q3 dot minus q2 whole square. Now here it's sort of obvious what the gauge symmetry is, because if you just find the variation here, it's going to be delta q2 dot minus e to the q1 delta q1, right? That's the beauty of the exponential. Its variation is simply, derivative is itself, plus q3 dot minus q2 delta q3 dot minus delta q2. Okay. Now, in this form, it's obvious what the gauge symmetry would be. Change q3 by any amount you want. Okay. So you get some solution of the Lagrange equations of motion here, which you can of course explicitly. This is also pretty straightforward actually, despite this rather horrible view. The Euler-Lagrange equations are actually pretty easy to solve here. And that this is a singular Lagrangian is also obvious. There is no q1 dot term. So the Hessian here will be 0, 0, 0 on the top line. In fact, it will be 0, 1, 0, 0, 0, 1 if you work out the full Hessian, right? And here it's obvious that you automatically get a constraint which comes from the first Euler-Lagrange equation. Since P1 is 0, if you write down the Euler-Lagrange equation for the first component, you are just going to get del L del Q1 is 0, which is an equation involving only Q's and Q dots. That is an obvious constraint. That is not the only constraint. There are other constraints which will come in. Okay? But to begin with, that's a constraint you can immediately write down. And the change that I'm talking about is just say change Q3 to Q3 plus delta Q3. And Q2, well, that should be obvious, to Q2 okay, what will that do? That will make this term go away, right? This term will vanish. Again, I'm not using the equation of motion here at all. I'm just saying if you made this change from one solution where you have Q3, Q2, Q1 satisfying the Euler-Lagrange equation of motion, change them this by delta Q3, change this by dgt of delta Q3, this term will go away. Okay, and what about Q1? Change it to Q1 sorry, I shouldn't really have gone that far to the corner, but this essentially, that will make the first bracket vanish, right? This one. You make delta Q1, I've just put in delta Q1 is equal to the minus Q1 times delta Q2 dot, and delta Q2 dot is second derivative of delta Q3. So give me any arbitrary function delta Q3, whatever you want, as long as it's smooth and twice differentiable. I just make a change in Q3 by that, change in Q2 by this, Q1 by this. Again, a time dependent change which I change, where I change everywhere Q1, Q2, Q3. And if your original thing had extremized the action, the new one will also extremize the action, because here, well, delta L is not even a total time derivative. Delta L is going to be explicitly 0 here. So no change in the action, right? Okay. Now I think since I have only 10 minutes, I will definitely not be able to work out the whole step-by-step procedure today, but maybe that 10 minutes contains the question time or? No. Okay, good. Oh, look, that's basically because I have a limited amount of material, and if it continues too far, people will get to know whether I don't know the stuff at all. So this reminds me of, like, you must have seen this famous QFT lectures, the Coleman lectures. In the middle of one of them, Coleman says, "Please ask questions, because if you don't ask questions, I finish my material in half an hour and then I'm very embarrassed," which essentially is going to happen to me too if I continue too long. Okay, maybe with what I remember of the material, I can go on for one more hour if they don't beat me up. But I won't. Because then I will run out of material on the last day. Okay, so procedure. Now things are going to begin looking a bit nasty, because notation becomes a lot of issue. Remember, you have this W which has a 0 determinant, rank RW, nullity, which is the dimensionality of the null eigenspace, n minus RW. So as we said, you have these vectors, I'm just writing q dot here to remind you that these are functions of q1 q dot, okay, which are 0 and alpha. There are n minus rw such. Okay, let me draw a line here so that this is a general theory that we are starting out with. Now, we already said this. What we will do is, first of all, instead of calling this W, for the general theory, I am going to call this W0. And to call this 0 semicolon alpha. No other reason except for the fact that this is a 0th generation thing. We will then have a 1th generation, 2th generation, and so on. So, I will put 1, 2 appropriately. Okay, so first thing that we learned about, from each of these V's, I should be able to figure out a 0th order constraint. Times EI, summed over all I. EI 0. EI zeros are basically the Euler-Lagrange equations of motion you get directly from the Lagrangian itself. Okay? Or just to make notation slightly better, dot E. So, these dot products gives me constraints. Okay. Now, there is one problem which might immediately arise. The constraints, of course, are that these are 0, right? The moment the equations are satisfied, E vectors has components which all vanish. So, on shell, all of these would have to be 0. And why are they constraints? Because each one of them depend only on q and q dot, not on q double dot, despite the fact that EI has q double dot, because the q double dot term comes with a wij, which Vi will kill. So, you will just have q dot functions. But the important question is, how many constraints do we have here? Remember, each of these vectors, Vi, the I of course is just a component. So, V vector has 0 comma alpha or semicolon alpha as indices. 0 just tells you that these are 0 generation, and alpha is the label. So, I have n minus rw a number of independent eigenvectors to start with. But the question is, are these going to be independent? It's still possible. Remember, the V vectors are independent, right? But when you contract them with the E, it might turn out that some of the components may ultimately end up depending on each other. Okay? Right? V vectors may be independent, but you are contracting them with E vector. Basically, it means you are contracting them with K vector. The W part does not contribute. So, this is basically okay, equal to 0 is basically on shell. However, it might turn out that for some of the vectors, these 5 zeros will be able to combine among themselves to give you a 0. That is, they become functionally dependent. Okay. Now, what that tells you essentially is the following. It tells you that you have a relationship between these EI components which actually vanishes not only on shell, not only when EIs are 0, but also when EIs are not 0, because that is just a condition between the VIs that you are putting in. Okay, so, that will be a condition which will vanish even off shell. But remember, delta A, the change in the action, is given by this. So, you have some combination of the EIs which vanish even off shell. Then if you take the delta QIs just by choosing them appropriately, you will make a variation which vanishes everywhere. That is the gauge symmetry. Okay? That is the 0th order gauge symmetry, if you have one. But that is not where the thing ends. Why? Simply because, okay, now at the end you will find a bunch of them which will vanish off shell. That is, some combinations will vanish, but the rest will be genuine constraints. This will actually vanish only on shell. Okay. By default, this looks like this will vanish only on shell, but some of the combinations may also vanish off shell, and those give you the gauge symmetries at the 0th level. The ones which vanish only on shell, those are genuine constraints. But now the question comes, will these genuine constraints take valid as time evolves? They have to, right? So basically, what happens now the notation becomes a bit messy. So basically what you have is among the V's, there will be some, let's call them W's. There should be some combinations which would vanish identically. So this is not just, okay, this 000 means vanishes everywhere. That's what will give you the gauge conditions. And apart from that, you will have a few which will give you genuine constraints. Now, each of these genuine constraints have to be valid at all times, which means their time derivatives will also have to be 0. Now, a constraint equation has what? Has q's and q dots. The time derivative will have q double dots also. So now you will have a new term which you add to the original set of equations. Now what you will end up with is a bigger W, that is more terms with the accelerations in them. Okay, let me just quickly illustrate that in 5 minutes with the example that we had, because all these words sound a lot more complicated than they really are. So just take a look at the example. So I unfortunately don't remember any of this, so I have to recalculate the whole thing. This was the one which had gauge symmetry, right? So what is E1? What was E1 for this? Does anybody remember what I called E1 0? Double dot plus y dot plus x minus y, and E2 0 minus x plus y, right? That's critically important here. And E2 0 was minus y dot minus x dot, sorry, plus y minus x plus x minus y, negative of this. Exactly. So my E0 vector was given by 1 0 0 0 x double dot y double dot. I'm just splitting up the acceleration term and the velocity term. This is the k, and the k vector is the rest of it. This is the k0, k vector 0th order. What is that? It's y dot minus x plus y and minus x dot plus x minus y, right? And if we follow the procedure, we want to find out the null eigenvector for this, which we already know, that's 0 1. Our v vector is 0 1. And taking a dot with, now I am not using the label alpha here because there's only one such, right? Here the nullity is 1. So I don't really bother with an additional label. But this is a v0, a 0th order thing. Okay? Now if I take this v0 and dot it with my E0, that gives me my phi 0, the only 0th order constraint, which is simply this equation minus x dot. Now for data reference, we need to keep track that this is E02. This vanishes, and this vanishes the moment the equations of motion are satisfied. This was of course trivial here because this was the second equation of motion. Minus y, of course, yeah. This is what trips me up all the time. Okay, so this is my constraint. Now, the demand that this constraint vanishes at all times adds one more equation. What is that? That's minus x double dot plus x dot minus y dot equal to 0, right? So to my set of Euler-Lagrange equations of motion, I now add a third equation which has an acceleration part and another part which doesn't have the acceleration. So this now gives me my E1. So that was E0. Now E1 basically has the E0 on top, whatever you had, these two rows are still there. In addition to that, you have to add minus x double dot plus x dot minus y dot. Okay? So now you have W1 times this plus K1. This is the 1th order. So what are those? So what is W1? W1, remember, now you have a three component object which you get by applying this matrix on a 2 component object. Of course, that's a 3 row 2 column thing. It's no longer a square matrix, of course. And what is this? The first piece is straightforward. The upper 2 rows are the same. You get one more term. What is that? Minus 1, 0. Right? Now, and K1, of course, is whatever you had at K0, the 2 rows, and below that you have x dot minus y dot. Right? That is the additional piece, additional acceleration independent piece, which comes from my third equation, which is actually a constraint equation, persistence in time. Right? Okay, now take a look at this. Can we figure out null eigenvectors for this? Now we are looking at left eigenvectors. A row vector which I multiply this by and get 0. That's pretty easy to figure out, right? A, B, C, if this is a vector, what does this tell you? A equal to C. And B could be anything. Okay? Right? Now, that means that generic thing is A, B, A. Right? Or it's a row, right? So I should write A, B, A. Now, the one we already had was 0, 1. That was a one we had at the 0th level. There was 0, 1. But the same structure here would be 0, 1, 0. It should be pretty obvious that if you start with whatever you had at the previous level and just put in additional zeros at the end, that will keep on satisfying the equation, right? That will give you a null eigenvector, because those additional zeros will just cancel out whatever additional rows you have put in. So this is nothing new. This one we are not even going to talk about. But I do have a genuine new eigenvector which I did not have before, which is 1, 0, 1. That's independent of the previous one. Of course, independent has to be taken with a slight pinch of salt here. After all, one was a 2 element row vector, this is 3 element. Here independent means you cannot get that by just padding it with enough zeros. Okay? So 1, 0, 1 is your new null eigenvector. So 1, 0, 1 contracted with this E1, the original E1, and this added together will give you a new constraint. Okay. And now the question is, does this give you a new constraint, or does it actually give you something which you have already seen before? Maybe some combination of what you already have. It's possible, right? Just because you're combining these two terms, you're definitely going to get a constraint. The question is it a new one? If it is, you proceed. If it is not, and in this case it will not be, we will do this calculation next day because I'm out of time. It will turn out that this vector is actually essentially the same as the original constraint. The moment you have that, you can figure out that there is a gauge symmetry lurking behind. How? We'll look at the detail next day. But the basic idea here is simple. You get the constraints first, 0th level ones. They have to be valid at all times. So their time derivatives also has to be 0. You just append them to your equations of motion and keep on working this until you run out of new constraints. Either whatever you get is already something you have already got, or whatever you get is a combination of what you have already got, or you get nothing. Or the other possibility is the null eigenvector that you get in the next stage are only the previous ones padded with zeros. No new null eigenvectors. Then you are done. So, this procedure ends in basically two ways. One, you run out of new null eigenvectors, at least essentially new null eigenvectors, or all the constraints you get are actually combinations of what you already had. In the second case, you will end up with gauge symmetries from that. How? We are going to talk about that next time. Okay, any questions?
In the first case, we won't have gauge symmetry. In the first case, we won't have gauge symmetry.
If you went through the end without ever getting any combinations, and you run out of new null eigenvectors, then you will not get gauge symmetries. It's possible that you may run out of null eigenvectors in the fourth stage and you have already got some combinations before. Then those combinations will give you gauge symmetries. Why those combinations will give you gauge symmetries is really rather obvious, but I have to sort of write that down and show you. But if at any stage the constraints that you get, even at the zeroth level, suppose you had two constraints and they were actually related to each other, that would actually give rise to gauge symmetry. That one is easy. Suppose it so happened that let's say your W was 1, 0, 0, 0, 0, 0, 0, 0, 0, let's say. Then 0, 1, 0 and 0, 0, 1 are both null eigenvectors. That means if you contract them with E, you get E2, 0 and E3, 0, these two components. Now, if it turns out that E2, 0 and E3, 0 are equal to each other, let's say. Not E2, 0, E3, 0, of course, they won't be equal to each other, but because E2, 0 and E3, 0 might have different acceleration paths. When you contract with a V, say phi 2 and phi 3 are equal to each other. What does it really tell you? That E2, 0 minus E3, 0 is 0. If you look back at your original variation in the action, you take delta Q1 equal to minus delta Q2 equal to minus delta Q3, then E2, 0 minus E3, 0 into delta Q will come out, and E2, 0 minus E3, 0 is 0, so that will give you gauge symmetry. So, at any given stage, if you have combinations of constraints which vanish identically, they will vanish everywhere, off shell as well, and you will get a gauge symmetry. If you don't get anything like that, and ultimately you run out of essentially new null eigenvectors, then you will not have a gauge symmetry. Not having a gauge symmetry is rather rare, basically because you have to go through this whole step without ever running into a new, without any of these new constraints running into an old one. We will illustrate this with the two examples that we talked about. In one case, you will run out of new eigenvectors, in the other case, you won't.
Sir,
Yeah.
in that case, when we dot V with this E0, V0 with E0, we are getting this phi 0, and which is identically equal to E2 0. So
Phi 0 is E2 0, but phi 0 is 0 on shell.
yeah, so that's why we can.
That's not a gauge symmetry, right? No, phi 0 is 0 when the equations of motion are obeyed. That means the equation of motion has a constraint. Some combination of positions and velocities have to be connected to each other on shell. And that also means that you can't put in arbitrary initial conditions. The initial conditions will have to obey those constraints. But that's not a gauge symmetry in itself. E2 0 equal to 0 is an Euler-Lagrange equation of motion. It turns out that, say, E2 0 minus E3 0 vanishes identically. Then what will happen is, the moment you make delta Q2 and delta Q3 equal to each other, you are going to end up with a variation in action which is 0.
But these conditions may not happen always, right?
No, the point is, if you have a singular Lagrangian, what is guaranteed is that it will have null eigenvectors. Eigenvectors, that is the Hessian will have a null eigenvector. Now, the EIs will always vanish on shell. So, the E vector, whatever you write down, will have to be identically 0 on shell. If you contract the E vector with the V's, these null eigenvectors, that will of course have to vanish on shell. There is no question about that because all the E's vanish on shell. But the moment you contract the V vector with the E's, in general, if you contract any vector with the E's, you will get accelerations and position and velocity. Of course, that will give you the equation of motion, the acceleration in terms of positions and velocities, right? But the moment you have vectors which are null eigenvectors of W, you contract with V, the acceleration part goes away. And you are left with a connection between Q and Q dot alone, which will give you 0 on shell. Those are constraints. So, constraints are, you have to get constraints the moment you have a singular Hessian. This det W is 0 automatically tells you that there will be non-zero null eigenvectors, which if you contract with, now of course that statement I made right now is not perfectly precise, in the sense that suppose 0, 1 had been your null eigenvector, and let's say e to 0 only had a y double dot, no x, y, whatever, then of course that will give you 0 equal to 0 identically, not a constraint. But that is a very unusual situation. In almost all situations you will get constraints, but do you get as many constraints as null eigenvectors? The answer is you may not. Some of those constraint equations, despite the null eigenvectors themselves being linearly independent, they dotted with the e's may give you things which are connected to each other, in which case you will get something which vanishes identically. That means not only on shell, but that connection will be valid everywhere, and that will give you a gauge symmetry. Then once you have a constraint, a genuine constraint, not a connection like this, that genuine constraint has to persist for all times. So differentiate that gives you a new equation. If at that stage you get a new null eigenvector with a bigger W, a new null eigenvector, new meaning not the old one padded with a 0, but something essentially new. If you have that, continue, you may get a new constraint, or you may get a constraint which is connected to the old one, or some of the constraints you get. After all, these were all very simple, where you had only very few null eigenvectors, but suppose you had 10 null eigenvectors, out of which 8 give you things which are connected and 2 gave you genuine constraints. Then those 2 will add to the equation of motion on the next stage, their derivatives basically. They will give you new eigenvectors to deal with, find out, and then this procedure continues until you run out of essentially new null eigenvectors, or every constraint you get is a combination of the old constraints. Whichever way it ends up, you end up, when you get combinations, those give you gauge symmetries. When you don't have combinations but just run out of eigenvectors, you don't get gauge. You have genuine constraints without gauge symmetries. So I will work this out explicitly tomorrow. Tomorrow will be rather boring in the sense that will be a lot of algebra. Okay. Some few examples where I want to show you the various possibilities explicitly.